In stats, we wrapped up conditional probability, and it's some of the more challenging stuff we've ever done. We have this Roger Federer problem here. Maybe skim through that. So we have two variables. One variable is listed first. If he makes first serve. And by the way, in tennis, if you miss your first serve, you can still win the point. So this is a touch biased if you're not familiar with tennis. So probability of making his first serve is 63. So they tell us that in that opening sentence. Always be aware of the word of. This happens in just a moment. But in this one, I do see the word of, but it's not limiting anything. It's just out of his first serves, 63% of the time he makes it. The next sentence is the one that is hard to read. So when he made his first serve, he wins 78%. That is a conditional statement. That reads in probability world as given he makes first serve, the probability of him winning is 78%. So we have two variables here, making first serve and winning. So those are our two variables, but that second sentence isn't just a plain old probability of 78%. And you should notice it when you make your table. So I'm going to make a table over here on the left. I don't know why I'm making it like this. Usually I just draw the grid lines. There we go. So if I put making his first serve right here, that means right underneath it, he misses his first serve. It's the opposite of making the first. And then up top, that means the other variable is win or lose the point. I see percentages, so let's move them to decimals and say 1.0. And that opening statement says that entire row of making first serve is 63. And hopefully you see something wrong with 78% going right here. Because this plus this should add up to 63. And I can't put 78 right there. So I could fill in this missing piece, but that's all I can do. I can't say more than that. But what I can do is I can use the formula of A given B to solve for the intersect of win and makes first. So let's do that over here. So I know probability of win given makes first equals the intersect of win and makes first divided by probability of making the first. So that's my formula. I just took what I wrote in the top left of the screen, A given B, and I translated it to this problem. Win given makes equals win and makes divided by makes. All right? So far I haven't done anything, hopefully, that complicated. Now I'm going to take that 0.78 and that 0.63, and I'm going to substitute in here and do some algebra. So instead of when given makes, I can write 78. I don't know the intersect of the two, so I'm just going to rewrite it. And instead of makes first, I can plug in 63. And if you still don't see what to do, maybe instead of that probability up top, write an X and just go back to algebra class. I'm solving for X. So let's multiply 0.63 on both sides. And I know when and makes first equals 0.63 times 0.78, which is 4914. We still have more information we haven't even read from the problem. So starting where you see purple, we have another probability. When he misses his first serve, he wins 57% of the time. So let's add that here. That's a weird looking 5. Let me try again. There we go. All right, I have a similar situation. I know that when given miss equals win and miss over miss. Let's substitute in. We know 57 can go here. I know miss is 37. And I don't know win and miss. So multiply both sides by 37, and we get it. We end up with 2109. So if you missed that, I went 0.37 times times 30. 0.37 times 57. And that gave me 2109, which goes right here. All right, then you can fill in the rest of the table. It's not that bad. Those two add up to 7023. When I subtract those values, 4914 from 63, I get 1386. When I subtract 2109 from 37, I get 1591. And those two add up to, my table was the other way, 2977. All right, then the questions below this are very easy after that. A whole other way to look at this, let me erase my table. So maybe hit pause if you didn't get it yet, is to make a tree diagram. So if you have room on your paper, maybe draw this instead. So let's make this in blue. When I read that opening sentence, I know that him making his first serve is 63. That means him missing his first serve is 37. This is called a generation of branches, and you make a generation for each variable. All right. So that first generation is him making missing his first serve. Off of that, write the second variable, and he might win or lose. Now, the tricky thing is second generation in a tree diagram is made up of conditional probabilities.
Students and teachers, please pardon the interruption. If you have a class in the 2100 hallway, 5th, 6th, 7th, or 8th.
All right, so second generation is made up of conditional probabilities. That means that top branch is when given makes. And that branch is 78. Each pair of branches, like all the scenarios, need to add to 1. So that means given that he makes his first serve and he loses is 22%. The next win branch is 57, and that is when given misses. That last branch is 43. So you can use a tree diagram if you want. That second generation of branches is made up of conditional probabilities. All right. We're going to answer some questions based on our table. So hopefully you have a table made, and we'll just read from that. This first question, probability that he makes his first serve and wins, is 49-14. Look at where they overlap, and it's 49-14. Probability that he wins is the very end of that, or bottom of that column, and that is 70-23. For the last one, use the formula if you want. Miss and win divided by all the wins is 2109 divided by 70-23, which is 3003. All right, we're going to move on to independence. So for independence, we have a rule we got to learn, and we'll apply it in the problem down below. So first off, make a note. This is not the same as mutually exclusive. All mutually exclusive means is that the intersect is 0. All right, independence is totally different. Totally different. And the formula is if events A and B are independent, that means probability of A times probability of B equals the intersect. That's one way to check it. Like they're going to ask us, as you see in the bottom, about left-handed versus right-handed, if events are independent. So that's one way to check. Like you plug in values and you see if the left side equals the right side. The other way to check, the alternate way to check, is to find the conditional of A given B. If A, probability of A occurring is the same as the probability of A given B, that means B had no effect on A, didn't change its outcome. That means they are independent. All right? So to solve lefties down under down here, you have to write the rule. You have to show the numerical values, and then say yes or no. So let's give it a shot. We have this census at school data on Australian students. Thankfully, we have a nice round number of 100 students. We have males and females, right-handed people, left-handed people, and they want us to show if being a male and left-handed are independent. So first off, I like to state the rule. If probability of male times probability of left happens to equal probability of being a male and left-handed, then independent. So let's find those values. Probability of male is 46 out of 100. Probability of left is 10 out of 100. Find where they cross. And that is at 7. And this is not enough. You need to plug into that formula. Even though you may look at it and be like, it's obvious they're not independent, you need to blatantly show with the formula that they don't equal each other. So 0.46 times 0.10 is 0.046, which is not the same as 7. Male, being a male, let's change this. Events, male and left-handed are not independent. All right. We'll save this sad space shuttle problem for another day. All right. Have a good one.